So in this video, we're going to ask ourselves, is it soluble? In the previous videos in this series, we looked at determining the concentration of a solution. And in that case, we made the decision that all things were soluble, meaning they could be dissolved. In this video, we're going to explore what does it mean for something to be soluble? So when reactions are conducted between two soluble compounds, meaning we have a beaker with solution 1, a beaker with solution 2, we're going to add both of these into a large beaker. Oops, lost half an arrow. What happens in the solution? So we are going to create a precipitate, which I'm going to draw as dark dots. And so this precipitate is going to be an insoluble compound, meaning it is going to be something different than the previous aqueous ion. So this is aqueous, this is aqueous, and then here we're going to have some aqueous and some solid. So our compound is going to change from aqueous into solid. So in order to do this, we want to think about what ions are in solution. So we're going to think about the polyatomic ions, and in this case, we are going to assume that all of these are going to be soluble. So sodium chloride dissolves into a sodium plus a Cl minus. Magnesium dissolves into a magnesium 2 plus 2 NO3 minus. So sodium phosphate is 3 Na plus PO4 3 minus. So you'll note that all of these have charges and the subscripts are important. The polyatomic ions live together, meaning the nitrate molecule still lives as a nitrate. It does not decompose into nitrogen and oxygen. So for aluminum sulfate, we have 2 Al3 plus and 3 SO4 3 minus. So in this case, all of these compounds fall apart. So what does it mean to be soluble? We also want to think about the solution of the ions. So if I have a 1.25 solution of sodium phosphate, what is the concentration of each ion? So we know that we have 1.25 molar of Na3PO4, and this decomposes into 3 Na plus a PO4 3 minus. So for every 1 mole of sodium phosphate, we have 3 moles of sodium and 1 mole of phosphate, which means that for the phosphate ion, it is 1.25 molar because the concentration is the exact same. In this case, the volume is the same. However, for every phosphate ion, there are 3 sodium, which means that this is 3 times 1.25, which gives us a total of 3.75 molar. So we can calculate this for any ion of any concentration. Basically, we need to take into account the stoichiometric ratio of the different components in the compound. So how do you know if something is soluble? Is it random? And the easiest way to know is that you just dump your chemical in some water and hope for the best. Or is there a pattern? So it turns out that there's a pattern, and it matters whether it is the counter ion. So some compounds matter how they are mixed together, and some compounds matter in other components. So it turns out that any compound that contains a nitrate ion is soluble, all of them. Across the board, there are no exceptions to that. If it has a nitrate, it's going to be soluble, meaning it will be aqueous as long as it's in water. However, when you have a phosphate ion, the majority of these are insoluble. So always keep in mind that some of these are determined as all are soluble or all are insoluble. It's kind of hard to tell which is which. But phosphate ions, we just looked at the sodium phosphate. It turned out that sodium phosphate is soluble. So when phosphate is mixed with these, it is going to be soluble. So this feels like a lot of information. So how can we think about this? So you can use a solubility table, which is provided in your document. So a solubility table is a pattern by which things are soluble. So you will see that sometimes it says soluble or insoluble, or it will say slightly soluble. So when we think about this, slightly soluble means that it is only partially soluble. So some of it will dissolve, but the majority will not. So we can start to use this solubility table to predict whether or not something is soluble. So let's look at these compounds. We want to ask ourselves, which of these are soluble? So if you look on there, we can see that silver bromide, insoluble. Sodium chloride is soluble. Silver hydroxide, not soluble. So why don't you take a moment to try to look at these other three? Find the ion, look in the solubility table, which you have access to, and predict whether or not they are soluble or insoluble. So now that we're familiar with using the solubility table, we can identify the product in a reaction. So right now we're going to think about identifying a product. In a moment, we're going to start to be able to predict what the products are. So if we mix together magnesium nitrate and sodium hydroxide, what we'll see in a very short moment is that the cations change partners. So the magnesium is going to hang out with the hydroxide and the sodium will make a compound with the nitrate molecule. But the question we need to ask ourselves is, which of these is the soluble product? Which is soluble, which is insoluble? So based on the solubility table, all nitrates are soluble. So this is going to be aqueous. The majority of hydroxide components are insoluble, so the magnesium hydroxide is a solid product. So this is the precipitate. And the precipitate is the product. And so shortly in this video, we will talk about why the aqueous solution is not a product. But we are going to use the solubility of the reactants to start to predict the products in a metathesis reaction. So metathesis is just a fancy word for a exchange of partners. So what we can see here, and I will use some components, is that AX is now with AY and B is now with BX. So what we did is the A and X separated, and the two cations now have different anion partners. So when we think about this, no matter what it is, if we can figure out what the components are on the left, we can predict what they are on the right. So let's look at some examples. So what are the products when aqueous potassium iodide and sodium chloride mix together? So in this case, we know that the sodium and the iodine are going to switch partner. Nope, the sodium and the potassium. So we will get sodium iodine plus potassium chloride. So when we look at this, we have to ask ourselves, are these both soluble or insoluble? So we know that potassium chloride, aqueous. It turns out that sodium iodide is also aqueous. So when both products are aqueous, as we're going to see in a little while when we start to look at the net ionic equations, this means that there's no reaction. Because the aqueous solution means that all of the ions present on the left are present on the right. So we didn't get a product. So let's look at potassium carbonate and nickel 2 chloride. So we are going to switch our partners. And so we're going to end up with nickel carbonate plus 2 potassium chloride. So make sure that you are following the rules of compound creation that we've learned previously. So we thus far are not balancing these equations, but we're going to get to that. So potassium chloride, as previously seen, is aqueous, and nickel carbonate is a solid compound. So this is solid. So if we were to write our balanced chemical equation, we would have potassium carbonate plus nickel 2 chloride aqueous. And that gives us 2 potassium chloride aqueous plus nickel carbonate solid. And there is no order by which these compounds need to be written in these equations. You could have swapped both of the reactants and swapped the products, but in the compound, it should be written anion, then cation. So far, we're just basically swapping these around. Are there easier ways by which we could do that? So it turns out that there are several different equations that we're going to use, and we're going to write most of these. So a molecular equation is, frankly, a complete, balanced equation. This basically means it's the same equation that we've been writing, but now you're going to generate the products. So a complete ionic equation shows all ions. So what we're going to start to look at is in the molecular equation, what ions are present for any of these aqueous components. And a net ionic, this shows only the ions involved in the reaction. So we are going to remove spectating ions. So we're going to learn about the spectating ions here in just one second. So we're going to be able to predict the product more easily than just thinking, okay, these two switch in this way. So let's look at this equation that we just wrote, where we have K2CO3 aqueous plus nickel chloride aqueous gives us 2 KCl aqueous plus nickel carbonate solid. So the reaction, or a complete ionic, is going to take all of these apart. Based on the polyatomic ions and all of our previous work, we know that the complete is going to take all of these apart into their components. So we will have 2K plus aqueous plus CO3 2 minus aqueous plus Ni2 plus aqueous plus Cl minus 2Cl minus aqueous. So this helps you figure out the components. We have to show the charge and you have to show the state. In order for all of this to work, this is an essential part of this. Now, for the products, we have 2K plus aqueous plus Cl minus 2Cl minus aqueous. Now, the nickel carbonate, because it is a solid and insoluble, it does not decompose into its ions, so it lives together. So the complete ionic shows you all of the different components. Now the net ionic only shows you what is present, not on both sides. So if we were to look at these equations, we can see that there is a potassium ion on the left and one on the right. When we see the same component on both sides of the equation, it can go away. So this is out and this is out. We can also see the chloride ions. And so we can rewrite this equation as CO3 2 minus aqueous plus nickel 2 plus aqueous gives us nickel carbonate solid. Because it turns out that the only thing that really happened in this component is that the carbonate ion worked with the nickel ion to give you a solid. The other ions, the K plus and Cl minus, are spectating ions. A spectating ion means it's not involved in the chemical process. So when we look at this, what we see is that the potassium ions and the chloride ions are not involved in any way, shape, form, or fashion. So let's look at another example. We are going to mix together copper bromide, and sodium hydroxide. So we're going to take our CuBr2 aqueous plus NaOH aqueous, and then we're going to figure out what the products are. I like to write the left-hand side of the complete ionic first. So we get copper 2 plus aqueous plus 2Br minus aqueous plus Na plus aqueous plus OH minus aqueous. So this makes it actually really easy to see how the copper interacts with the hydroxide, and that's going to give you CuOH2 plus NaBr. We don't know what the states are yet, but the molecular equation needs to be balanced, and it's currently not. So when we put a 2 here and a 2 here, now it is balanced. But don't forget, those stoichiometric coefficients must go in part of the complete ionics. We put a 2 here and a 2 here. So based on the solubility tables, copper hydroxide is solid and sodium bromide is aqueous. So now we can add that copper hydroxide, solid, plus 2 Na plus aqueous, plus 2Br minus aqueous. From here, we can cancel out our net spectating ions and rewrite our net ionic equation as Cu2 plus aqueous plus 2OH minus aqueous. And that's going to give us copper hydroxide solid. Oops, I forgot it too. So we can create any of these for any given component. So let's look at another example. So in this case, we have hydroiodic acid and barium hydroxide getting mixed together. And we know what the balanced chemical equation is. We get 2 moles of liquid water and 1 mole of barium iodide. So the complete and net ionic equations for this are a little bit different. We don't have a solid product. It turns out that you don't have to have a solid product. Your precipitate can be gas, solid, or liquid. None of these come apart. A product just can't be an aqueous solution. So let's look at the complete. So we're going to have 2H plus aqueous plus 2I minus aqueous plus barium 2 plus aqueous. Oops, got a little ahead of myself, so let me erase that. Plus 2OH minus aqueous, and that gives us 2H2O liquid plus barium 2 plus aqueous plus 2I minus also aqueous. So from here we can cancel out our spectating ions of the iodine ion and the barium ion to where we see this equation, 2H plus aqueous plus 2OH minus aqueous. And that gives you 2 moles of H2O liquid. So we are going to see this equation in the next video when we start to think about acids and bases. And so in this case, I, on the written exams, would accept this or the simplified version of H plus OH minus gives you 1 water. Either of those are acceptable in my opinion. So now we can predict the products in any metathesis reaction, and we can figure out all of the other components.